Welcome to Mathlink Academy, where we connect the dots. I am Mr. C, and in this unit, we're going to talk about concavity, concave up and concave down of functions, and also talk about the inflection point. So let's get started. Before we do some examples, let's at least get a definition of concavity. And in this case, it says, let f be a differential on an open interval I. The graph of f is concave up. This would be our first example, concave up or concave upwards on the interval I when f prime is increasing on the interval, and concave down or downwards. This is downwards on an interval I when f prime is decreasing on the interval. So in other words, we're basically saying we want to find when is the function going upward as concavity and going downward. It's going to look like this, concavity. Now to find the concavity, we have to use the test for concavity. For f, be a function, let's say f is a function, we want to find the second derivative, if it exists, on that open interval I. If f prime, and that's where we're going to look, f double prime, in this case, f double prime is greater than 0. So you got to find the second derivative, and where it's greater than 0 for any x value in that interval, then we're going to say it's concave upwards. Similarly, we're going to find the second derivative. Again, this is the second derivative, and I'll clear this so you can see the double prime. When the second derivative is less than 0 for all value of x in I, then we say the function itself, the original function, is concave downwards. The reason why we say greater than or less than 0, because basically this is saying for the top piece, when the second derivative is positive, that's what it means, greater than 0, or non-negative, I should say in that case, then it's a concave up, and less than 0, we're talking about non-negative, we're talking about negative values. If it's negative values, then it's concave downward. So really what we're looking at, and I'm going to clear this so you can see this, is when the second derivative is positive and when the second derivative is negative. We want to look at those values, not necessarily the numbers, but when it's positive and negative, it tells us if it's concave up or concave down. So let's look at an example and show you how to write the answer from concavity. So here's a function on our whiteboard, and I want to show you how to find concavity if it's concave up or concave down, and show how to write the answer to show that it's concavity up or down, the concavity of it. So the first thing we're going to do, we're going to first find the first derivative, and then we're going to find the second derivative. So to find concavity, we must find that second derivative. So the first derivative of this will be x squared minus 1. That's our first derivative. Then we find a second derivative. How we find that? We look at the first derivative and take the derivative of that. This will give me 2x. Once you find the second derivative, you set the second derivative, 2x, set it equal to 0, and then solve for x. This will give us some critical points. In this case, x will equal to 0. For that to happen, x will equal to 0, and that will give us possibly point of inflection. We'll talk about that later, how to write the point of inflection and what it means to have a point of inflection. But for right now, we'll just talk about concavity. So here's our critical point using the second derivative. And just like we did with the first derivative test, we're going to make a number line, and we're going to use those critical points or point, in this case we have 1, to create different intervals. So in this case, we have 2 intervals, interval 1 here and interval 2 here. So we have those 2 intervals, and we're going to choose numbers that are less than 0 and numbers that are greater than 0 and plug it into the second derivative. So make sure we plug it into the second derivative. And the second derivative is underlined in orange because we're looking at concavity. We're plugging the numbers in the second derivative. So pick a number less than 0. So let's say -1. So f double prime of -1, we plug that into our second derivative. That gives me a -2. I don't particularly care about the number itself, but just the sign. And so in this case, in this particular region or interval, we have negative. Now you do the same thing for a value greater than 0. Let's pick a value greater than 0, plug it into the second derivative. F double prime, plug in 1, plug it into the second derivative. 2 times 1 up here will give me 2. Again, I'm not particularly caring about the number itself, but what the sign is, and it's a positive sign. So what this is telling me that in this first region, this is concave down because it's negative, and this will be concave up in that region, which is positive. So how do we write the answer for concavity? It's similar to what we did in increasing and decreasing. So let's rewrite our values here. Here's 0. And we said before, I have to look back to make sure I do the right values. This was negative, is that correct? So this is concave down. These values are positive. This is concave upward. Now, in our case, there's something happening at 0, and 0 is actually an inflection point. And so those critical values that we have for the second derivative will give us those inflection points. We'll talk about that later. We're not going to talk about that now, but at least put that in the back of your mind. And so to write our answer, we say is concave down and we use our x values from negative infinity. Again, we're coming from negative infinity all the way to 0. That's when it's concave down. And it's concave upward, concave up from what? From 0, it's in that second region, from 0 all the way up to positive infinity. And that's our answer from concavity. And that's how you write the answer. Now to find the points of inflection, you may have more than one point of inflection on a graph. You have to look at how the concavity look at that point. So the first thing, for a point of inflection, you have concave up on one side of the point and concave down on the other side. The key point is they will keep the same slope, which is your first derivative. So your slope will remain the same on both sides of the point, but the concavity would change. Again, I'm going to say it again. Your slope remains the same, but your concavity changed, and that gives you a point of inflection. Some points of inflection are very easy to see on graphs, others are not. That's why it's good to do it algebraically so you get the right answer. So in this case, let's look here. This point that we have, I'm going to show you in red. That's right here, this point. That is a point of inflection. We want to write that point of inflection. One side is concave upward, the other side is concave down, and that's a point of inflection at that point. But also I want to show you this. The slope, and that's just taking one point, no matter where it is, the slope in this case is a positive slope on both sides. I'm taking a tangent line on those curves on both sides. And notice those red lines, those are tangent lines, supposed to be one line on both sides. They both go in a positive direction. They're going upward. And so the slope stayed the same, but the concavity changed. Let me show you another example. Here's another point of inflection. you see the point, and you see that one side is concave down on the left side, which is right here, and this is concave up. And where they meet is called the inflection point, or the point of inflection. Now I want to ask you, what is the slope in this case? What is the slope in this case? Again, to find those slopes, you have to use the first derivative. So somewhere the first derivatives help us out. So the slope, so I'm using a tangent line here. Let's put a point here, tangent line here. So this is, again, a positive slope, but on one side is concave down, the other side is concave up. It's opposite to what we just did with the first example where you had concave up, concave down with positive slopes. So let's look and see if I can draw a nice one. So here's a point, and let's say it's concave up here and it's concave down. Now, that point that I just drawn is an inflection point, a point of inflection, because that's where it defines that. But if I pick a tangent line on that curve on both sides of the point, it's going in a downward slope. It's going downward, and that's a negative. And so the slope stays the same on both sides. It's negative, but then we also have the different concavity on both sides, which shows us a point of inflection. Where this is a negative slope, these first two are positive. You may want to give you an exercise. Draw another point of inflection on your own that's different than what I've drawn, where it has a negative slope. That'd be a good example for you to try and do that very quickly. Now, here's the point of inflection. This is how we're going to define it, or how you want to write the answer. If C is a number, is that point, let's say C is that X value on the point of inflection, then F of C, you got to plug in that into the original equation. F of C is a point of inflection. You give the X and Y value when you give the point of inflection of the graph of X. Then either F prime, double prime, again, F double prime of C is equal to 0, or F double prime does not exist. When F double prime equal to 0 or F double prime does not exist, it gives us those possible points of inflection. The key I'm going to keep saying is, don't forget, it's not only when it's equal to 0, the second derivative, but it's also when it does not exist. That also can be a point of inflection, the second derivative. Now let's go back to our whiteboard and did our first example. Our first example was find the concavity of f of x. And so I just put f of x and box it in the blue so you can see that's the original function. Now, when you want to find the concavity, you also want to find those inflection points. And then what we did before, we found the first derivative, and that gives us a slope. That's important right there. And the second derivative give us that concavity, help us find the concavity. We found out that x equals 0 when we set the equation equal to 0 and solve for x equal to 0 is a point of inflection. That's basically what we found out. We found out going to our next slide was concave down and concave up. And since 0, and we only have 1 point in this case, we want to plug that 0 into the original equation to give us that f of c, so give us that y value. So you plug the 0 into the original equation. Now our original equation is 1/3 x cubed minus x. So our original equation is f of x is equal to 1/3 x cubed minus x. Plug into the original equation, so f of 0 would be equal to 0 minus 0, 0. And so a point of inflection is 0, 0. That is our inflection point. And a lot of people will put POI to talk about a point of inflection. Now notice the 3 checks I have. I have concavity, the concave down, concave up, and a point of inflection. Now we can graph this. So let's graph this. And looking at what we have here, we have our point of inflection as 0, 0. We have concave, and I'll do this one, concave up and concave down. Let's go back to what we wrote down before. The concave up is from 0 to infinity. Concave down is from negative infinity to 0. And we can sketch the graph. How will we sketch the graph? Let's draw an X and Y axis. Again, this is a sketch. 0, 0 right here, that's 0, 0. That's our point of inflection. And what we see here, we see there's a concave from negative infinity to 0. We got a concave down. So it's looking, and again, this is a sketch. We're looking at something like this, and then a concave up from 0 to infinity. So this is kind of a zoom in lens of how it looks at 0, 0. And 0, 0 is our inflection point. Notice that our slopes, or these tangent lines that I'm putting right here, are positive. And so the slope is always going to be positive. So this is a positive slope on both sides, but one side is concave down, and then the other side is concave up. And that's a point of inflection. Let's do another example. It says determine the point of inflection and discuss the concavity of the graph of f of x equal to x to the fourth minus 4x cubed. So the first thing we're going to do is find the concavity, and we have to find the second derivative. And then from those critical values that we get from the second derivative, it should help us find those point of inflection. We possibly can get a sketch of the graph if we want to do that also. So let's look at how we can do this. So I'm going to write on our slide, and then if we need to go to the whiteboard, we can do that too. So first thing we need to do is find the first derivative. The first derivative will give us 4x cubed minus 12x squared. Not too bad. Now let's find the second derivative, because that helps us with concavity. And just to go back, if you want to look at previous videos or other videos that I have, the first derivative helps us find increasing and decreasing, actually those slope pieces that I was talking about earlier in this video. Now the second derivative gives me 12x, if I'm not mistaken, square minus 24x. And now we got to set this 12x squared minus 24x, set that equal to 0, and then solve for x. So we could take a factor out of 12x. What's left in the bracket will give me x minus 2, if I'm not mistaken, equal to 0. And we got two values, x equals 0. That's from that 12x equals 0. And we're going to have x equal to a positive 2. Those are our points of inflection right there, 0 and 2. And we're going to see how the concavity first, and then write the points of inflection second. So let's go to our whiteboard to show you how to do the remaining part of this problem. Now, looking at our problem, the second derivative is in the red, and our first or original equation, f of x, is in the black. So again, like we did before, we're going to use that second derivative to help us find the concavity. If I'm not mistaken, our critical points were 0 and 2. And what we need to do is plug in values that are less than 0, between 0 and 2, and greater than 2 into the second derivative. That's why I put the number line under the second derivative. So let's pick a number. I'm going to do something a little different. I'm going to pick a number less than 0. So I'm going to say a negative 100. That's definitely less than 0. If I plug that into, and I'll show you the work, then I'm going to erase it, the second derivative, like a negative 100, and I'll put it in factor form. That gives me 12 times a negative 100. That's a big negative number, times a negative 100 minus 2 is a big negative. So you have two negative numbers. When you multiply two negative numbers, it's going to give you a positive. Again, I don't care what the number is. I want to care about what the sign is. So that's using a negative 100 in the second derivative. Let's use a number between 0 and 2 in the second region in our second derivative. So a number between 0 and 2, 1. Plugging 1 into the second derivative, 12 times 1 is 12. 1 minus 2 is a negative number. So a positive times a negative gives us a negative number here. Then we'll do a number bigger than 2. Let's do 100. 12 times 100 is a large number. 100 minus 2 is a very large positive number. Multiply two positive numbers, we get a positive. So this is in the second derivative. So what this is telling me right now, this region is going to be, since it's all positive, we're talking about concave up. It's going to concave up, concave downward, concave up. Now we found our concavity. So let's write that down. So it's concave upward. I'll just say up for right now. And our answer is from negative infinity to 2. And also the last region, the third region, 2 to a positive infinity. It's concave down. I'll put down. Understand the concavity between 0 and 2 because that's where it's negative at. Now we've done the concavity. Let's put a check there. Now we're going to do the inflection points. So we're going to use those two numbers, 0 and 2, and plug it into the original equation. So notice I'm going to plug this to give me my y value and this into my original so I give my y value. So make a note of that. So as I do that, I'm going to put this in black, f of 0. That'll give me 0. So 0, 0 is 1. And then let's plug in 2 for this here. That gives me 16 minus 4 times that, 8, 32. I think that gives me a negative 16. So when we plug in 2 for x, we get a negative 16 as a y value, if my math is correct. And these, I'm going to put these in curly brackets. That's my curly brackets. That's how they look. Are called points of inflection. And these are point of inflections, and I'm going to put a check there. Now, if you want to sketch the graph of this, one of the things you'll also want to find is the local extremums or the extremums. Are there a max and min in this problem? And when you get the max and min, you get a better chance to get a graph that looks like what you can graph on the calculator. So looking at this, I'm going to show you something. Let's go back and let's write down these on a new whiteboard. So we have our concave up, concave down, and then let's put a point of inflection. Again, I'm going to just give you, and if I remember my point of inflection, I'm going off the memory. I think we had 0, 0, is that correct? And we also had 2, I think, negative 16. Now let's look at our concavity. Concave up was from negative infinity to 0. And then also 2 to infinity. And then the concave down was from 0 to 2. So let's at least get a sketch of it. It's not going to be perfect, but you at least got an idea once you have these. And again, I can't emphasize, you want to make sure you find the extremums, the relative extremums. So let's see what we have here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I may go by 2s with the y-axis. So it makes me, since I have a negative 16 there. So the first thing I would do is plot the points of inflections. So we got 0, 0. I'm going to do this in blue. So 0, 0. That's that one. And then 2, negative 16. We'll go by 2s. 2, 4, 6, 8. So 2, negative 16 is right here. And then the second thing is then do the concavity, concave up or down. So from negative infinity to 0, is concave up. So it's going to look something like this. Again, we're just sketching a graph. And then it's going to go concave down here from 0 to 2. And then it's going to go concave up to the remaining part. So that's the sketch of our graph that we have. I believe our graph, again, I'm going to write down f of x, and you can pause this and graph it and see if it's similar. See if your calculator gives something similar. It's x to the 4th minus 4x cubed. Now in this case, right here, I have a minimum value. And we understand if you want to look at some other videos that I've talked about increasing and decreasing and finding relative extremums, you can use the first derivative to find this min or max. In this case, we have a minimum, and we want to find the x value and also the y value by plugging into the original equation. And so that's the sketch of our graph of those concavity and also the point of inflection. Now, we saw how to find the concavity and also the point of inflection. Just for a quick minute, I want to show you another procedure called the second derivative test that will help you find extremums. So this is another test using the second derivative that will help you find max and min. So we call this a second derivative test. So let's get started. The second derivative test. So let f be a function such that the first derivative of c is equal to 0. Those are our critical points that we have. Okay. And before I show you that graph again, the second derivative test of f exists on an open interval containing c. If that exists, if the second derivative exists, we can do the second derivative test. If the second derivative, when you plug in the c value from the first derivative, is those critical values, I'm saying when you plug in the critical values into the second derivative and it's greater than 0, it's a positive number, we have a relative min right off the bat. You know it's a relative min. If it's less than 0, you have a relative max. If you plug in that critical value into the second derivative. Now, if it's equal to 0, that second derivative, you plug in the critical value in the second derivative is equal to 0, then the test fails, okay? So looking at that. So let's look and see how we can use the second derivative to find these extremums as max and min. So let's look at in this case, the drawing of what 1 and 2 saying. If f prime of c is equal to 0, if you find a critical value through the first derivative, plug that value in the second derivative, and if it's greater than 0, it's a relative min. And that's how a relative min looks. And then a relative max will be plugging in that critical value and it's less than 0. They want to give you the work yet, guys. I'll give you that work in a second. If it's less than 0, then it's a relative max. So make sure, and a max look like this, and a min looks like this. We'll look at the example I'm about to show you. So find the relative extremums. That's all we're going to do. We're not going to worry about concavity or inflection points, but show you how the second derivative test works and help you find relative extremums. So the first thing, we're going to find the first derivative. So the first derivative would be of f of x will equal to a negative 15 x to the 4th plus 15x. That's the first derivative. So let me put down, that's f prime. And from there, let's set that equal to 0 to find the critical values. I know you said, Mr. C, you emphasized that word critical. Yeah, I know. And so we factor out, let me factor out a negative 15x. And I'm left with here x cubed, if I'm not mistaken, plus, in our case, we have here 1 is equal to 0. Okay. Now, looking at that, we want to solve for our critical value. So in this case, x would equal to 0 coming from the first one, and it looks like x would equal to a -1. So we have this critical value. We're making sure, so let me make sure I factor correctly and have these right values that we have for our critical values. Okay, so I made a little corrections because I remember this should have been 15x squared. And a lot of you saw that earlier. So notice I'm highlighting this is x squared. And if I take out an x squared, a -15x squared, we factored out on the third line, that leaves x squared plus 1. So I'm good with this. X is equal to 0, you're right, comma, and then x will equal actually two numbers, plus 1. In this case, we got x squared. Let me make sure I make this correct, guys. Because this should be a minus. We got x equals plus or minus 1. So we end up with 3 critical values. And we'll do this on our whiteboard to give us more spaces. I don't want to make a mistake on this since I don't have a lot of space. So our critical values, we have 3 of them. 0 and x equals plus or minus 1. We're going to plug those critical values in the second derivative. So again, let's go to a whiteboard, make it a little more clean, and then you can see the work to find these relative extremums using what we talked about earlier. So here's our original problem, and f prime was -15x to the 4th plus 15x squared. I want to make sure I write that correctly. Our second derivative will be 4 times that is a -60x plus 30x. And this -60 should be x cubed. Okay. Now, when we did our factor form and we set the first derivative equal to 0, we found x values of x equal to 0 and x equal to plus or minus 1. And that came from the first. I'll write that in blue. So that came from the first. Those are called our critical values. And then from our critical values, we're going to plug that into the second derivative to see if it's positive or negative or equal to 0. If it's equal to 0, the test failed. If it's positive or negative, it's either max or min. So an easier way to do this, I'm going to look at the second derivative, and let me just factor out. I can factor out a 30. Let me factor out a -30x. That will give me here a negative, I believe, 20x squared minus, in this case, -1. Okay. So let me actually underline that right there. Now what I'm going to do is I'm going to plug in different values, those 3 values in the second derivative, and it's going to tell me. So let's try f double prime and plug in 0. So I plug in 0 using this first one into the second derivative, and I put it in factor form to see what we end up with, to see what happens. We end up with 0 times some number, which is 0. So in this case, the test fails. Now, let's plug in the second derivative, the number -1. We'll do -1 first, and then we'll do +1. So when I plug in a -1, in the second derivative, I'm looking here, this gives me a negative value, positive, and then this gives me that. And so it gives me a value that would be greater than 0. If it's greater than 0, that says that is a relative min. Remember, if it's greater than 0, it's a relative min in the second derivative test. Then let's plug in the value 1. Plug in 1 into the second derivative. This is our second derivative. Either way you want to do that. Gives me negative, gives me a negative number plus that. And excuse me real quick, guys. This actually, the first one, the negative one, excuse me, will actually give me a positive, a number greater than 0, like I said before, which is a min. And then for 1, it will give me a negative number less than 0, and then that is a max. So all you have to do is find the y value. So we know that -1 and then 1, and you got to find the y value by plugging it into the original equation. This -1 gives me a minimum, and the +1 gives me a max. And again, you want to plug that into the original equation. You can do that. So you plug in 1 into our f of x. I'm going to go back up here. -1. That gives me 3 plus a -5. So it'll be 3 plus a -5. In our case, is a -2. So I'm going to erase that line. So this gives me a -2. And then you plug in 1 into the original equation. And so 1 would be a -3 plus 5, which gives me 2. And there they are. And that's using the second derivative. So very quickly, we went over concavity by using the second derivative and also using the second derivative to find the point of inflection. And then using the second derivative test, you can also help find your extremums, your max and your min. Again, if you have any questions, feel free to go over the video and look at some of our supplementary material on our website. Again, let Mathlink bring it together.